Now A comma B trees will indicate you always formally an AB tree is a multi-way search tree such that each node has between A and B children. Each node always in between A and B children. It will not exceed of this. Whereas in the other trees, what we were talking about in the previous slide, it will uses at most 2 children, or there are many constraints from one data structure to the other data structure. But as far as this AB trees are considered, you will be going to see the children of each node A and B, and stores between A minus 1 and B minus 1 items, where A and B are integers. By setting the parameters A and B approximately with respect to the size of the disk blocks, a data structure can be derived that achieves good external memory performance. Now, an AB tree where A and B tree integers such that to satisfy the condition 2 less than or equal to A less than or equal to B plus 1 by 2 is a multi-way search tree. And the properties are size property, depth property. Size is each internal node has at least 2 children unless it is the root and has at most B children. So this 2 I'm indicating with. I'll take an example and I'll show you how it works. So depth property is what? All the external nodes have the same depth. That means all the leaf nodes in the tree will be same level. Right? Now we'll take some example and we'll show you. Let us assume that 2, 4 tree. Now 2, 4 indicates you what? 2 is A, 4 is B. Fine? So 2, 4 tree in the sense that your tree should have 2 children minimum and maximum 4 children. Okay? And so that means A is equal to 2, B is equal to 2A minus 1. A is what? Minimum number of nodes in a tree. B is what? Maximum number of nodes in a tree. This is the condition. When you are talking about 2, 4 tree, 2 indicates you minimum number of nodes, 4 indicates you maximum number of nodes. That means A is equal to 2, B is equal to 2A minus 1. Now, so AB tree is what? Which made up of nodes which contain keys that are always sorted from left to right. So this is what a simple symbolical representation, the AB tree. That means if you see here, we'll take an example and we'll move forward. So let's understand about that. I'm taking here 1, 3 nodes. That means, so here you can see 1 is represents as A, 3 represents as B. So I told you in the previous video, previous slide, that A represents minimum number of children, B represents maximum number of children. So that's what you could able to see. Minimum number of children in this tree is 1. 1 children. This is also 1 children. Okay. Now, so 0 is the only node. 2 is the only node because it can have only 1 and 3. At most 3 because B value is 3, so it can have at most 3. And A value is 1, so it can have at least 1. And the order of this is each key separates 2 subtrees. You given with the 2 keys and each key separates 2 subtrees. The left one containing keys that are smaller and the right one containing keys that are larger. And that is the reason why I have given this symbol. Always it will be in the same constraint. that arranging of AB tree is left will be left to right, you can see in the sorting manner. Now, so that's what each node has a number of children which are determined by the parameters A and B. A is minimum number of children a node can have in the tree. B represents maximum number of children a node can have in the tree. Now you can take some example that when you look at this example, you will be finding out many things. That one of the thing is what? All leaves node on in the same level. If you see, now let's see 1, 3. Now the way how I organized this 2, 4 tree. 2, 4 tree represents what? 2 nodes should be the least. 4 is most. So each node will be having at least 2. The reason why it is not 2, 4, why come it is 1, 3, why come it is 1, 3, because I have arranged the tree such that the elements ought to be arranged left to right, sorted manner, right? So 1, 3 is in the root position. Now, so 0 may not be indicated always in your examples. When you look at the textbook examples, 0 may not be there, but you can consider 0 also for the better clarification that I wanted to show. It will be having a sorted manner. So if you don't have 0 also, if you begin with the 2 node also, it's okay, no problem in that. So that means your tree will be represents with 1, 3 and 2 and 4, 5, 6. Now, so in 1, 3, A is 1, B is 3. So what is the maximum and minimum number of nodes in a tree? A is greater than or equal to 2. That means number of nodes in a tree should be 2, right? Greater than or equal to 2. So that means less than, at least it should have 2 nodes. So root node, this node can have 2. Root node can have 2. And so here 2 is the other node which are having 2. Again here I have 3 nodes. Why it is 3 nodes? Because B sounds it is maximum number of nodes in a tree. So I'm taking now here I'm taking 4. Why the reason I'm taking 4? Because the node value here it is 4. Okay, so I'm taking 4 nodes. Now, so here A value always will be greater than or equal to 2. B greater than or equal to 2A minus 1. Now, so the complexity of this is what? If I wanted to search any key, let's suppose that I wanted to search 4. How searching operation will be done is, I am first of all comparing with the root node. So in root node I have 2 elements, A element, B element. So I am comparing 4 with A element, match not found, 4 with B element, match not found. Then it seems to be greater than of this B. So obviously we will not go to this. As the moment when you find the matching with 1 to 4, when you found it is greater symbol, you will not come to this side. You will go to this side. So for searching of 4 element will happen to be in the right part. So we'll come to right part and the same operation will takes place. Again you will be searching this 4 with the 4. Now match found element is there. If you wanted to take the other element, that we'll see. So it is what a basic searching operation. Now what operations are possible? Searching, insertion and deletion. So what is the complexity of this one? Earlier to this trees, there are many data structures with what we can do external searching. That are what AVL tree and binary search tree, R and B trees. Of course all these trees are binary trees only. Now, so the comparisons of this is what? Logarithmic. That means log n. So why log n I said? Because when you wanted to search any key, you will not going for both the sides. You will be coming when the element is found to be lesser number than A, you will be finding the element in the left part, hence you will not go for right part. We'll see with the example and you will come to know. if I wanted to search 5 element in this tree, now how searching operation will move, I'm comparing key element 5 with the list of elements. So that means 5 1 double equal to 5. Now is it? No, it is not. Condition fail. When condition fail, we will again search with the whether it is less than or greater than. If it is less than, searching operation happens to be at left part. That means this part will search. If 1 is greater than 5, search operation will be at right part. Will be go this side. So it doesn't take n comparisons, it's take only logarithmic comparisons, that means log n. So as far as I wanted to search this key element which is 5, now we will not come to left side, we'll go to right side. So right side element is 3, match not found, will fall to the right subtree. In the right subtree also the same process will follow. 5 is equal to 4, no. So we don't go to this side, and again 5 is equal to 5, match found. So you found the element with log n comparisons. Now if it is a successful search, if I wanted to search the element which is not found, then we'll happen to be come down to the leaf elements. So that means element is not found. Now we'll see how insertion can be taken place. It is also very simple. See that after every searching, after every insertion, after every deletion, you have to maintain the AB tree constraint. That constraint is what? Elements has to be arranged in sorting manner. Always you have to keep in mind, in such a way you have to make this tree order wise. Now, so I am taking the example of 1 3. That means I'm working with the same example. I am not changing the example. In the same example, I wanted to insert 5 element. So how can I insert 5 element? Already 1 3 is there, right? 1 3 0 2 4 5 6 7. 5 is here, correct? 5 is here. So I'm saying it is invalid. Why it is invalid? Because as far as A comma B tree rule is concerned, you should have only at most B children, or at most B nodes are possible. So here 1 comma 3, it have only a single node. As far as this side concerned, it should have only 3 nodes, but it have 4 nodes here. What we'll do is, we'll shift this 5 to the root place. That means it becomes 1 3 5. So when it becomes 1 3 5, now 4 has to be get part of this, this field, right? So that's what 0 2 4 6 comma 7. Now again 0 will be having 2 children, 2 2 2, and it can have 3, because as far as B value concerned, it is 3, at most 3. Now it is balanced. So now I can say it is balanced of A comma B tree. Let's see, if I wanted to insert 7, then will it be a balanced one? Again we'll see that. So what we'll do, 1 3 5 and 7 will get part. 7 is already there, I'm sorry, 8 I wanted to insert, 8. So when I wanted to insert, I will be inserting at the side of this. So when I insert 8 here, nothing will happen, because it is still balanced, because at most you need to have 3 children. So 1 3 5 0 2 4 6 7 8, still it is correct. There is no problem with this. Now problem comes when you wanted to insert the other element in the same tree. Then you have to split the tree. The reason, you should shift this 7 to top again root. Now root is having what? 1 3 5 7. So that means your B value is what initially? 3. It should have only 3, but it is exceeded to 4. Now you have to split it. How you have to split? Send 3 to up. That means 3 up, 1 5 7. 0 2 4 6 8 9. So this is what perfect A comma B tree. Now, so here you can write it is 0 comma 3. So splitting condition is what? Splitting a node makes the 2 resulting nodes have at least B plus 1 by 2 children. So this is about A comma B tree, and the complexities of A comma B tree is what? For searching, because it can be a successful and unsuccessful search. So we will take logarithmic comparisons for all the examples. So this is about A comma B tree, which uses to have external searching in search engines. Thank you all.